Welcome everyone to the next edition of our Prague Cohomology seminar. Today our speaker will be Leonid Ryvkin from Lyon, and he will talk to us about vector bundles over unordered configuration spaces, which is joint work with some of his colleagues from Lyon. So Leonid, please go ahead.
Okay. Thanks a lot for the invitation. I'm very happy to speak here. And so the thing I'm going to talk about in some sense for today will be a purely geometric construction, but our motivation for it actually comes from physics. And basically, the motivation is the following. In a certain field theories in physics, your state space, so the states of a physical system, are described as the section space of a certain vector bundle. So E2M is a vector bundle. And then we would like to talk about observables, which means that we would like to understand the smooth functions of the space, so of the section space. Now, there are different ways to do so. One of them would be to start introducing differential calculi for Frege spaces. However, this space of functions turns out to be huge and very difficult to control. What one can do instead is trying to find subalgebras in it, so I'll call it A, which are smaller and easier to work with.
So full is space of the smooth section.
Yes.
And you consider smooth function on this space.
Yes.
So that you say that you supply the space of smooth section, the infinite dimensional manifold structure, right?
Yes, and I basically want to avoid that, so I don't want to talk about this space at all. Instead, I'm going to look at smaller spaces where working in a differential geometric way is going to be easier. There are people who, I think that Fredenhagen and Reisner, who really, and others who really describe the smooth structure here, but I'm not even going to define what exactly I mean by that because I'm going to pass to much smaller, easier to handle spaces. And now one can ask questions of what should this A, which we haven't defined yet, satisfy? And the first thing we could ask for example, so requirements to A. The first thing we could ask for is it should contain the linear functions. So we would like, if we take gamma m E dual, so it's a Frege space, it has a continuous dual, it's the space of distributions. We would like it to be an A. Today we were not going to focus very much on the subtleties of distribution. So one thing we could kind of require instead, just to have some approximation of this statement, is we could take the sections with compact support in the functional dual of E. So the functional dual is the dual of E, tensor the density bundle on M. So densities are, if the manifold is orientable, this is isomorphic to volume forms. So this is something we need to integrate because when we want to think of a section like this as something which we can apply to an element of Q, we pair them, we obtain a density, we integrate over the whole manifold, and that gives us the functional. So in practice, in the physical context, we will actually do something else because we would like things like the Laplacian to be inside. And so we don't really want just to be able to have expressions in E, we want to have expressions in its derivatives. And we want those expressions to not necessarily be linear, but we would like to allow them to be polynomial. So maybe I'll use a color for that because we won't really use it today, but it can be done. So, or rather, we would take, rather take the sections with compact support of, and now we take jets of E, so Taylor expansions. And then we allow the symmetric algebra to have polynomial expressions. And then we would take the dual of that, and that's still something we can integrate against any element of Q. Oh, yeah. So this is somehow physically relevant, but most of what we are doing, I will continue working with E, but the E could easily be replaced by this. It's still a vector bundle. There are some issues with finite dimensionality, but it's somehow, in each practical situation, one only takes finitely many derivatives and finite polynomial expressions, so the infinite dimensionality is somehow not grave. You can formalize it by pro-finite manifolds, so projective limits of finite dimensional manifolds, or infinite manifolds, which are inductive limits. So kind of the infinite dimensionality problems which appear here are rather of a technical nature and can be solved. Okay, so we want this to be in A, and the moment where we allow those expressions, the map from A to functions on Q stops being injective. So maybe I'll write a map here, because this description would allow us some redundant information which we want to be included in the formulas. Okay, so one thing which would be reasonable to require of the algebra A is A to be commutative. So A should be commutative. We are here at the level of classical field theory. The observables in classical field theories should commute. One example, what we could do with what we have already seen is that we say, example, symmetric algebra over R of this space. Or of another space. Or of this other space. So we have a space which should be in the algebra. We just generate the symmetric algebra of it. And through the universal property of the symmetric algebra, we would map into the smooth functions on Q. The third condition, and this is somehow where, which is the main motivation for our work, is, maybe I continue on the next board, so everything stays visible. We would like the algebra to be geometric, and this is somehow a vague statement. So A should be geometric. And this is somehow mostly to say that the symmetric algebra of the sections of the vector bundle, it stops being a geometric object. It's formal sums of geometric objects, but we cannot really identify it with something which is geometric itself. And this is something which one kind of thinks one can easily solve. So if we just say that starting from E over M, we can build over M to the power of K, the kth external tensor product of E. So the fiber over a point x1 to xk of this new vector bundle is ex1 tensor, ex2, and so on, until exk. And if we just take the section spaces of all the mk's and with the values in the duals of the ek's, then we get an algebra. So from gamma mk e check k compact support gamma ml compact support el. We do have a natural map to the composed one, which is just, I don't know, we have something in k variables, we have something in L variables, we put it together, we have something in k plus L variables. So basically, if we just take the big sum over all integers of those spaces, that would give us an algebra. The problem is that this algebra is not commutative. Basically because phi of x, psi of y is not the same thing as phi of y, psi of x. However, this difference, it's purely on the level of sections. If we integrate against this or we integrate against this, it doesn't really change anything. So this is a virtual difference, and the constructions we are going to do in the sequel are exactly to resolve this technical issue. So goal, unite criterion 2 and 3 by replacing m to the power k with unordered configuration spaces. Okay, so this is somehow the background motivation. What will now follow is I give a quick introduction into what are configuration spaces, and then do the construction which we need to reformulate the algebra A, or to phrase the algebra A in their terms. Other questions at this point? Okay, so definition. The ordered configuration space of k points in M, it's just k points in M, which are all different. So we are removing M1 to Mk in case there exists an I which is not equal to J with Xi is equal to Xj. So we're removing the partial diagonals. This is an open submanifold in Mk. And then on this open submanifold, the symmetric group acts freely and properly, so the quotient is still a smooth manifold. And as before, we just put all of them together, so we will write uconf M for the disjoint union of uconf K. Okay, so this is already a first little defect of the theory because we're kicking out the diagonals. In what we are doing today, this will not cause us any problem because they're a set of volume 0. So when we only look at elements of this sort, we will not change values of integrals by that. If we go to the distributional side of the picture, this is a change, and we would need a different resolution strategy. We would need the space of multi-configurations, so Mk divided by Sk, possibly a desingularization of it. But this is a work of a PhD student in Lyon currently, Haichao Nguyen, who's kind of figuring out the diagonals so we can also do the distributional version of this. Okay. Maybe I'll just give a few examples of configuration spaces, even if just to note that they can be complicated, even if the departing space is easy. So, okay. Conv 0 of anything is just the set that contains the empty set. It's a 0-point configuration. There is exactly one of those. A 1-point configuration is a point in the manifold. Those are the only things we can say in general. A configuration of k points in R can be parameterized as follows. We look at the bunch of points, we take the very leftmost one, and then we just save the distances to the right towards the next ones. So it would be R for the leftmost point, and then R greater than 0 to the power k minus 1 for the distances towards the next points. If we didn't remove the diagonals, this will be greater or equal to 0, but it's getting a little bit complicated because the symmetric group action stops being free. So it would be a little bit weird as a space. Okay. Then configuration space of 2 points in S1 is the Möbius strip. This is primarily relevant for saying that we start with an orientable manifold. We take its unordered configuration space. It stops being oriented. So we don't have a choice. We have to work with densities, which are behave well on non-oriented things. We cannot work with volume forms. There is a really nice way geometrically to see it. One takes S1 times S1, the torus, writes it down as a rectangle, removes the diagonal, has pieces, one pushes them around in the right way, and one sees in the end that one has the topological diagram for a Möbius strip. It's a fun thing to do. Okay. More generally, maybe I could say that because S1 is a group, it's a little bit simpler. So this will always be a bundle of simplices over S1 in general. So the configuration spaces of S1 are still quite nicely to handle. Okay. So maybe one observation already now. The space of smooth functions or continuous functions or whatever functions on the unordered configuration space of M is a commutative algebra using the shuffle product. So F, maybe I'll write it with the sh symbol, G on some element. The elements of the configuration spaces are just finite subsets of the manifold, and I'll use subset notation most of the time. So it's the sum over all subsets of S of F evaluated at the subset times G evaluated at the complement of the subset. So this gives us a commutative algebra structure, and in a certain sense, what we'll try to do now is formulate a framework where we can do this for functions, for sections in vector bundles instead, so with coefficients.
But just to understand, S is now just a tuple?
Well, it's a tuple up to order. So
yeah, tuple up to order.
So assume S is in, oh, here it's an F. So S is in uconf M, which is in bijection to finite subsets of M.
Okay.
A tuple after, so yeah.
And then you just take these partitions into S and P. Sorry, in P and the complement of P, and then some overall. So is it correct to say that this is the formula that you get by basically taking representatives of F and G as functions on the configuration spaces before they were quotiented, then multiplying, and then just symmetrizing with respect to all of the arguments. Is that
Yes.
give you the same thing?
Yes. So if we think of S to be M1 to MK, it will be the same thing as taking the sum over all shuffles or unshuffled depending on your conventions. So sigma in shuffles in I, K minus I, and we are actually also summing over all possible I, F applied to the tuple M sigma X sigma 1, M sigma 1 to M sigma I, and G applied to the rest of them.
Right. And then there's the unshuffled, I mean, the version with no shuffles, just taking all permutations of.
Yes,
of
but then you
elements.
would rescale usually. I think it might not be. Yeah, so it depends on how you normalize things, but you could do it with all permutations if you liked. But then, of course, you have some redundancies.
Yeah, because the permutations, they act trivially on F and P. Okay, thanks.
Sure. Okay, I think I'll erase. Mm. Okay, so basically our goal is now to mimic, to create a vector bundle in which we can formulate this. Here we are somehow treating powers of the same vector bundle, but if we want it to fit into a nice mathematical structure, what we would like to is applying some sort of tensor product to two different vector bundles and getting a vector bundle on more points, even if the individual ones are not the same and are not coming from a vector bundle over M. So formalizing this, it's the shuffle tensor product. So we start with a vector bundle over uconf M and another vector bundle over uconf M. And I'm going to construct it component-wise, so I'm just going to fix two numbers of points here. We have a vector bundle, which we will denote by V shuffle W over uconf I plus J M. And it's defined as follows. Its value over a point, which is point of length Mi plus J, will be the direct sum over sigma, again in the shuffles, Ij, of V of the first bunch of points, tensor W over the remaining points. So V M sigma 1 to M sigma I, tensor W M sigma I plus 1 to M sigma I plus J. Okay, so set theoretically, this just works. Of course, we are in differential geometry, so this should be now a well-defined vector, a smooth vector bundle over this space, so one has to kind of go into local coordinates and check that it's actually a smooth vector bundle, or alternatively, and this is somehow the strategy that Haichao is currently using, you first define the vector bundle on the ordered ones, and then show that it's an equivariant vector bundle. And the way he's doing it is you can somehow create a geometric version of the Schur functor of how you get from a representation of Si times Sj to a representation of Si plus j. And this is kind of, if you write it down with respect to the unshuffles, it gives you exactly the same thing. So this is somehow, this is the by foot way of doing it. If you want to include diagonals, the conceptual one is certainly better. Okay, so this is a vector bundle. And it induces, so this Schur is an operation which takes two vector bundles over the full configuration space, and just by kind of going through all possible combination gives you a new vector bundle over the full configuration space. And this turns out to be a monoidal structure on vector bundles over conv. So Schur defines a monoidal structure over on vector bundles over uconv M. A monoidal structure is not only given by the product, it also needs a neutral element, and the neutral element is, so the unit for the shuffle product is the vector bundle which over conv 0 is R, and over all the other components is the zero vector bundle. So the only technicality, often people define vector bundles to be of constant dimension. We only need locally constant dimension, so constant dimension over fixed configuration spaces of k points. Okay. So now on this VB uconv, we have two monoidal structures. We also have the usual monoidal structure, and it turns out that those two play well together. So theorem VB uconv with tensor and tuple is a two monoidal category. I will not write down the full definition of two monoidal category. It can be seen as a monoid in the two category of monoidal categories or something like that. So there is like a short abstract nonsense version to define it, which one does not really see anything. And then if you unfold the definitions, it's 3 pages of diagrams, which is, okay, one is a monoidal structure, the other is a monoidal structure, all the coherences which you can put together in reasonable diagrams fit together. I think the essential piece of information, which is somehow linking those two, is the shuffle operation. So, and the shuffle operation is something which goes from AB shuffled with CD and goes to AC tensor B shuffle D. And so this is called shuffle for because it mixes the two tensor products and has nothing to do with the fact that we called one of our tensor products shuffle tensor product. Basically, this type of condition, intuitively, it comes from Ekman-Hilton type arguments. So you think of A, B, C, D to sit in a square. A tensor B, shuffle C tensor D, and you want to be able to map to the otherwise ordered shuffle. Okay. The reason why the two monoidality is interesting is that there is an approach to getting from classical field theory to quantum field theory by Borcherds, which is formalized using two monoidal categories by Stanislaw Herskovich. So somehow we stay in a framework which eventually in the future hopefully will allow quantization.
As you defined, is it an isomorphism? Is that the idea?
It's not an isomorphism. In our case, if you just write down the components, it will be an inclusion. So this one will have more components than those ones.
Okay.
Inclusion or projection, because actually you can give it two monoidal structures depending on what you prefer, and the map would go either one way or the other way, and it's just an inclusion or a projection, depending on preference. I think that when it is an isomorphism, maybe you can show that the two tensor products are the same. I'm not completely sure about that. So if they are symmetric, maybe like you need some other little conditions, but this is exactly the Ekman-Hilton type argument of you have two group structures, and maybe if the units are the same and certain rules are fulfilled, then they are the same structure. Okay, so now that we have this monoidal structure, we can kind of construct the usual objects in the category. So we can just take a vector bundle E over M, see it as a vector bundle over the configuration space, which is just trivial outside the configuration 1 part, and apply the functor which generates you usually the tensor algebra or the symmetric algebra. So, so we start with the tensor algebra, tensor shuffle E is just defined as E shuffle E shuffle E shuffle E k times when we are on the kth component, and then the full tensor algebra will just be the direct sum of the individual parts. When we do this, we appoint x1 to xk. This thing will have as a fiber all possible orders of ex1 to exk. So by the way we constructed it, we have redundant copies. We have v tensor w and w tensor v in the original definition. So t shuffle e over a point m1 to mk will be a direct sum over permutations of e x sigma 1 tensor 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 ex m sigma k. So on this we of course have an action now of the symmetric group of order k, which permutes the factors, and if we divide out this action, we obtain the symmetric algebra bundle. So symmetric shuffle E will be tensor shuffle E divided by S. Oh, I see. Sorry. S, where S is just the symmetric group of order k when we are on over k points. Again, the way how this will be done long term will be a little bit more conceptual, using S modules in the algebraic sense and then kind of transforming them to the geometric. But you can also look at it manually. Okay, so we can look at this. So the tensor algebra contained all possible permutations of the fields. Now we are dividing them out. So this S shuffle E over a point actually contains exactly one copy of the tensor product. It's just that because we don't have an order in the points, we also don't have an order in which element of the tensor product comes first. If we want to say it formally, if we denote by Q the projection from Oconf K to Uconf K, then Q star of, let's say, the kth component of the symmetric algebra will be E external tensor product E and so on restricted to O-conf k. So this is what live on m power k usually, and we are restricting it to the subset. So if, and this is again the work of Haichang Nguyen, if we would keep the diagonals, then the symmetric group action on this object would stop being free. We would have isotropies. So we would get a sort of singular vector bundles where, for example, when all points coincide, you have the full symmetric group acting on the fibers. And then there, the vector bundle dimension collapses, and you would get the symmetric algebra already kind of in the usual sense. So somehow interesting things will happen here on the singularities. Okay. So now we have a category in which we live. We know what symmetric algebras are. And now we can use as a first application, which is actually necessary for the field theoretic applications later. If we take the symmetric powers of the densities on M, we get exactly the densities on uconf M. So basically this symmetric shuffle construction which we did, it's compatible with integration, and this is something we'll need in a second. And so basically how to orient the diagram best? Yes. So we have this algebra C infinity of Q. I'll write gamma ME because Q is long ago. We have the compactly supported functions in the functional dual of E, which we can map into it, but we can also first generate the algebra of it and then map it into it. Let's see. Okay, so those were the spaces we had before, and now we want to replace it with something on the configuration spaces. And what we can quite easily show, because we basically constructed everything so we have a well-defined shuffle product. So we have the algebra of unordered configuration space of M. Where is it? Conf M with values in the shuffle of E dual. And because of the previous lemma, I don't have to put brackets which operation I do first. The problem is this one, while it is an algebra, doesn't have an integration because we didn't require compact support here. So what we would like to do is we would like to just say, okay, we take the unordered configuration space sections with compact support. There, no problem, we have a map, but, and we also, but we have two problems. One of them is, this one is not an algebra. And the other one is, we don't have a map from this algebra into it. So, and the reason why we have this is rather of technical nature now. It's basically because we removed the diagonals. The product of things with compact support doesn't need to have compact support. So, for example, you start on a compact manifold, S1. You take the constant 1 function and the constant 1 function. You multiply them, you would get the constant 1 function on the second configuration space. It doesn't have compact support because the second configuration space itself is not compact. So this removing the diagonals to avoid singularities bites us at this point. If we would want to avoid it, we could now start looking at factorization algebras here. Because if we multiply two functions which have disjoint supports, it means exactly that it's supported away from the diagonal, and we can stay in the same algebraic structure. So here, kind of side branch, which we are not following today, factorization algebra. I'm sorry, I'll mute it and I'll see how much time I have. 20 minutes, perfect. Okay, so because of our trying to make our life easier and avoiding singularities, we run into a new problem, and the rest of the talk will be one approach how one can try to resolve this problem, how one can find a space in between. So we are looking to a space in between, which is an algebra, and which still can be integrated. Okay, so the way we are going to resolve it is we are going to replace this, the notion of compact sets, which we would be using here, with the notion of bounded sets. And so the mathematical formalization of bounded sets is done through bornologies, which originally have been used in the context of functional analysis as an alternative to topological spaces. One can work with bornological vector spaces. However, more recently, people have also used them more directly in geometry by looking at, it's related at bornological topological spaces in general, constructing cohomologies for them. It's related to coarse geometry and so on. So we can also just kind of introduce the abstract notion of boundedness, like the abstract notion of openness in a topology, and work with it on an arbitrary space. So, definition, a bornology on a space X is a subset of its power set. So, like a topology, it's a system of subsets, such that subsets of bounded sets are bounded. So maybe I'll write it in formulas. A subset B in the curly B implies A is in the curly B. So subsets of bounded sets are bounded, and finite unions of bounded sets are bounded. So A prime in B implies A union A prime in B. And then there is a rather technical condition to avoid weird phenomena, which is points are bounded. So the first example of bornology is you take the bounded sets in a metric space. Another possible example is you take any topological space and you take the pre-compact subsets in it. So the subsets whose closure is compact. So this bornology has multiple nice properties. One of them is that it's a topological bornology. So there is a notion of compatibility between topologies and bornology, which is something like every bounded set has bounded closure, and every bounded set admits a bounded open neighborhood, which I'm not going to write down, but so this is topological bornology. And another nice property which it has is that it is completely described by a countable number of bounded sets, which in general need not be true. But so there exists bi in B for I in the natural numbers, such that such that B in B implies that there exists an I such that B subset BI. So this is not in general true for a topological space. This is something which is true if X is, for example, a manifold. So if X manifold. So this property says that I have a kind of an exhaustion of by countably many bounded sets.
Bounded sets in the metric space.
Yeah.
Like this countable property, I think it makes sense.
Yes, there it's always satisfied because in a metric space, okay, the distance between 2 points is always finite. So if you take just kind of bi, the ball of radius I around your starting point, then you will get the whole space.
Yeah, but why I keep it kind of abstractly is it avoids some other kind of pathology.
So sorry again.
So at the abstract level, defining bornology abstractly, so this countability avoids some kind of problems, pathologies?
So in the general definition, we don't really need it. In what we are going to do in a second, we are going to need it. So this is kind of an additional property. It's not a property of a general bornology.
This is you're imposing it.
Yeah, so this is after the example, it's somehow things that are satisfied in this example.
Okay.
Sorry, yes. General bornologies don't have those properties. I think for the bornologies to some topological vector spaces, it's already not true. Okay. So the reason why we will need this property is that when we construct the Fréchet space of smooth sections or of smooth functions on a manifold, the way how we find the countable number of seminorms to assure that it's Fréchet, which means that the seminorms defining it are a countable number, is by using a compact exhaustion. And somehow this is abstracting away this property for the context we are going into right now. So, and also general bornological spaces need not be topological. One nice implication of it is that the pre-compact sets are in the bornology. Okay. So, we call a map bornological if images of bounded sets are bounded. Maybe a map is bornological if a map F, if F of B is in the B of the target space. And that's something we'll use in a second. Okay, so the reason why we use the bornology is because removing a set of measure 0 will not change a lot about the bornology. So basically, when going back to those unordered configuration spaces, if we take two functions with bounded support and multiply them, then we'll get something bounded. But this is true, not if we take the bornology of precompact sets, but if we take the induced bornology from m to the power of k. So we start with m to the power of k. We go to O_conf km. So we restrict a subset of a bornological space has a natural bornology, basically the same bounded sets. So subset bornology. And then we go to the quotient uconf km. And now we take the quotient bornology, which inherits all nice properties we had before, because this map here is low, it's a covering map. Like near every point you have finite fibers. It's somehow so quotient bornology. So, and the bornology we get here, it contains the pre-compact sets, but it has more sets. So the bornology here contains more than the pre-compact set. Okay, so now we're going to use this formalism to define an appropriate space of functions. So we have again our vector bundle on M. The one way to define the Fréchet structure on this space of smooth functions is fixing a Riemannian metric and the connection and the metric on the vector bundle. So we fix some metric on M, we fix some connection on M, we fix some metric on E, and we fix some connection on E, which and now usually we would define semi-norms on the sections. So, but now because we have given some bornology on M and not just the pre-compact sets, this gets a little bit more subtle. We look at we define semi-norms from gamma E to R together with infinity, which are indexed by an integer I and a bounded set B. And they're defined as follows. So maybe F is now a section of the vector bundle. And now what we take is the supremum over all the points in B of nabla applied I times to F absolute value. So here, when I apply the first nabla, it's a map from gamma E to gamma T star M full times E. If I now if I want to apply another connection to it, I need both the connection on M and on E, because a connection on Tm induces a connection on T star M. So this is what allows me to iterate the process. So if I apply it I times, this will be have I slots for covectors and then one slot for E, and then I need the dual metric of G and H together to say what the absolute value of this is. And if B were compact sets or pre-compact sets, then this value would always be finite because this is still a smooth section. But because now we are generalizing to bounded things, the value might be infinite. And so we define the set of bounded sections of E to be just the F such that F IB are finite for all E, for all I and for all bounded sets. Because the bornologies I'll be using are exhaustive, here I could just take one of the countably many semi-norms. So on this space now they are really semi-norms, then value infinity is not attained. So we get IB are semi-norms. And one can carry out a calculation which shows that this space is actually a Fréchet space. Moreover, it has, so the way one does it actually automatically constructs a continuous map into all the sections. Because the bornology on M that we'll be taking is topological, it contains all compactly supported sections. And in fact, there is somehow a nice space in between, which a little bit replaces the compactly supported section space. It's the gamma M, let's say B, BB, E. So those are elements here with bounded support. So bornological sections with bounded support. And the same way how this space, it's not quite Fréchet, it's an inductive limit of Fréchet spaces. The same is true for this space. So the topologies on them are still quite reasonable. Okay, I have around 3 minutes?
Yeah, 5.
5 minutes, okay, perfect. So actually, yeah. So basically, I can now go back to this diagram. And now I can replace the question mark with the space of sections over uconf M, which are bornological and have bounded support of the same bundle. And this indeed is an algebra, because products of bounded sets are bounded, and we are taking bounded support, which in MK would be compact support. So being able to integrate is also assured. And this is somehow our answer to the initial list of questions of what is a nice subalgebra of C infinity of gamma E to consider. So gamma uconf MBB. Couple product of E dual is a commutative geometric in a certain sense. So, algebra naturally mapping to T infinity of gamma E. Okay, and I think I'll stop on this. Thank you very much for your attention.
Okay, any questions?
Yes, I have a question. Yes, so what is the application of this?
So,
Yeah.
so our goal is to describe observable spaces of field theories. Because we removed the diagonal, most kind of realistic physical field theories cannot be covered yet. This is what we hope soon the PhD student will tell us how to do. We can cover some topological field theories with this. So there are certain field theories where basically where you can get along without distribution. So where you can do everything with smooth functions, and where actually nothing interesting happens on the diagonal. You would have, for example, propagators there. So certain distributions which actually are represented by functions which have a jump discontinuity. And this is what this formalism is very good at describing. We remove the diagonals. When we integrate, this doesn't lose any information. And by removing the diagonal, we remove the jump discontinuities and can work as before. So we hope to be able to describe the observable spaces in those contexts. Long term, this two-monoidal structure suggests that this is a nice framework to do a certain quantization. But this is somehow something I cannot yet, I don't really understand enough yet to say anything competent about. It's just that apparently this Borchardt quantization approach uses two monoidal structures, and now we have a geometric description of that.
So I have a question. Common subalgebra of functions on the field configuration space are so-called regular functionals. So these are just polynomials in linear functionals, right?
With derivatives potentially.
Yeah. So linear functionals, which are written locally as an integral of a smooth density times any linear combination of derivatives of the field, right? So
this is only local ones or also non-local ones, which you describe like that?
well, what distinguishes from the clear?
Regular functionals local for you?
I didn't use the word local.
Yeah, that's why I'm asking.
Okay. It doesn't matter?
Okay.
I think it doesn't matter for my question.
Okay.
Wait, I haven't asked the question yet.
Sorry.
Yeah. So so regular functions are polynomials in linear functionals with these smooth densities, which I think they will belong to your class, but I think you have more. So exactly how much more do you have? This is my question. So the point where I see the biggest difference would be at the diagonals that you have removed. So if you took one of these regular functionals and removed these diagonals, then in the neighborhood of the diagonals, it would have very regular behavior. So basically, you would be able to fill in the values on those diagonals. But the way that you're defining your functions here, I think they seem, using these bornological norms, they would have to be bounded as they approach these removed diagonals, and their derivatives have to be bounded, but like they don't need to be extendable to the diagonals. Is that right? So how can you characterize the local behavior of the functions of these functions that are included in your formalism near the excluded diagonals?
So first of all, maybe saying that somehow again to include the regular functions, we would add jets and the usual symmetric algebra here,
Right.
and then somehow there is suddenly a natural map. So what happens near the diagonals is complicated in a certain sense. So we clearly get really more. So even if I take, for example, I take S1, and I would take S1 minus the North Pole, and I take the induced bornology, and then I would take the smooth bornological functions of it. So I take gamma v of S1 minus n. Then the bornology doesn't have any clue about the fact that the left side and the right side belong together. So what we would get would actually be the smooth functions on the closed unit interval, essentially, or like 2 pi interval, depending on your normalization. So we really get more in a certain sense. I think that we also, I think that we also probably get a little bit more through the fact that we are doing the symmetric algebra construction inside the section space and not just algebraically outside. So there is this, usually people take those functions which are basically products of local functionals, and then they do a certain completion. We don't have a proof yet, but I would expect the completion to lie inside the space we define. I cannot say if what else is swimming in there. Like there could be something even more, but I'm not sure about that yet.
Would you be able to say something about the wavefront sets of these of your observables?
So
maybe I can clarify for those who don't know what I'm talking about. So each one of your observables, so you take one of these sections from this tensor extended bundles over configuration spaces, and you can basically lift it back to the unquotiented or so ordered configuration spaces and bundles over them, and basically you can pair those sections with several copies of a certain field configuration, right? And that is going to give you your observable once you integrate. And any such quantity you could have a priori represented as a distributional integral, right? And for distributional integral, you can compute its wavefront set. So if you take one of your observables, what could you say about its wavefront set?
So the thing that I have shown today don't include the distribution. So I've done everything in smooth sections. You could, of course, somehow add an additional line below. You take somehow this, you take the space of bornological sections, you dualize it because it was a Fauché space, you have a nice space of distributions. The problem is that this does not behave really well with respect to the product structure, because once you are in distributions, removing a point can change everything. So if you had before that a Dirac delta on this point and you remove this point, then you lost all information in a certain way. So, so I think that to talk about wavefront sets, one will have to do the more complicated construction, which includes the diagonals, desingularize them, and work there. I think that usually the singularities of which appear in field theories are exactly on the diagonal. So I don't expect to see a lot of it here.
Well, some singularities are, I mean, they are on the diagonal, but the singular behavior is, it appears as kind of the growth of the function as it approaches the diagonal, right? So it's kind of singular at the diagonal, but you can detect the singularity by the asymptotic behavior as these smearing functions approach the diagonal. But in the example that you gave with the circle, sorry, maybe let people see where you're standing. The example that you gave with the circle, if you take one of these, elements of C infinity of the closed interval, such that at the sides of the interval, the values of the function don't agree, and then you kind of go back to the circle and integrate that against the field configuration, you will get a distribution.
Yes,
right?
so we can see
you have some distributions.
Some very mild distributional behavior, which is essentially that of jump discontinuity.
Right.
Yes.
Okay.
So those we can model, and this is what occurs in those in some examples, I think, by Cattaneo and collaborators whose names I unfortunately forgot, which actually gives an example where this formalism without going to distributions directly is enough. But yeah, I think, yeah, I cannot say much, anything competent yet about wavefront sets in that context.
All right, thank you. All right. So if there are no more questions, there are no questions from online participants, then let's thank Leo again.